So this is History of Mathematics Lecture 2. We started Chapter 1, and the great theorem in Chapter 1 is Hippocrates' quadrature of a particular lune. So let me first explain again what the word quadrature means. So the quadrature of a geometric figure or shape or object, whatever you want to call it, in the plane is a square with the same area as the figure. So we showed on Monday how to construct the quadrature of a rectangle. And the construction in Greek geometry, in Euclidean geometry, is construction using only a straight edge, which is not a ruler, it's unmarked, and a compass. So it's fun if you can actually do these constructions at home on a piece of paper, and of course you need a compass. And as I put into the notes or on Blackboard, you can buy a compass from Staples or from Amazon for $2.59. And just to test the system worked, I ordered this compass on Amazon. It was delivered the next day, yesterday, and it cost $2.59. That's pretty good. So let me see if I can use this compass to carry out the quadrature of a rectangle. And in order to do this construction, you have to know certain things. For example, we already proved that an angle inscribed in a semicircle is a right angle. Let me just draw a careful picture to show that. So suppose this is going to be my center, and I put my compass there. Let's see if I can draw a circle. That's pretty good. And with my straight edge, you'll see that this straight edge isn't marked. So I'll just draw any diameter. And I'll take any point on the circle or on that semicircle. And one of the axioms in Euclidean geometry is you can draw a straight line between any 2 points, namely you put your straight edge between the 2 points. So that's one side of the triangle, or one side of the inscribed angle. And that's the other side. And by the theorem we proved Monday, that's in the book, this angle is a right angle. A second fact that we need is with a straight edge and the compass, we can construct the perpendicular bisector of any line segment. So what is a perpendicular bisector? So here's a line segment, AB, and a perpendicular bisector. Well, there's a point that's called M between A and B, which divides this line segment into two equal pieces. And you can construct a line perpendicular to AB through this midpoint M of the line segment AB. So this red line, that's the perpendicular bisector of A and B. And how do we know we can do that in Greek geometry? Well, let me describe a construction right now. So without doing anything special, I will just draw an arbitrary line segment. Doesn't have to be parallel to the sides of the paper. That's a line segment. Actually, the way I've drawn it, it's too big for this piece of paper. So this is A, and this is B. And how do I construct the perpendicular line segment? Well, again, one of the axioms in Euclid says that given any 2 points A and B, you can draw a circle with one of the points as the center and the other point as giving you the radius. So let me draw a circle with center at A and radius equal to AB. That's the circle. And let me draw another circle with center at B and radius also equal to AB. And you see these two circles intersect. They intersect at that point, I'll call it C, and this point, which I'll call D. And using my straight edge, I can draw the line between C and D. And then one can prove that, in fact, where this line CD crosses the original line AB at the point M, that is the midpoint of A and B, and this angle is a right angle. And it's not hard to prove this in various ways. For example, if I were to draw these lines, AC, BD, AD, and BC, what can we say? Well, on the circle where the center is A and the radius is AB, this is a radius and this is a radius. So they have the same lengths. And on the circle with center B and radius AB, the radius is the same, and BC is a diameter and BD is a diameter. Sorry, is the same length. So these four sides are the same lengths. So if you look at, for example, triangle CAD, that's that triangle, and triangle CBD, these triangles have three sides, corresponding sides the same lengths. This equals this equals this, and this is shared. So these are congruent triangles. So this angle equals this angle, and this angle equals this angle, and this is an isosceles triangle, so these four angles are equal. In the same way, if you look at the top triangle and the bottom triangle, the top triangle is triangle ACB, and the bottom triangle is triangle ADB. They share a side, and the other two sides have the same lengths. So these are congruent triangles. So this angle equals this angle, and this angle equals this angle. And if you use the fact that the sum of the angles of a triangle is 180 degrees, if we call this angle alpha and this beta, then this is alpha and this is beta. And this angle is 180 minus alpha plus beta, and this angle is 180 minus alpha plus beta. So these two angles are equal. And 2 times gamma is a straight angle, 180 degrees, or pi radians. So gamma is pi over 2 radians. So this is a right angle. And these triangles are congruent, so AM equals BM. Anyway, geometry is very nice. Greek mathematics is very important. And this is a Greek construction of the perpendicular bisector of an angle. Okay, so let me go through again the construction of a square with area equal to that of any given rectangle. So let me start with a clean piece of paper, and let me construct a sort of a random rectangle. So that's a rectangle. And let me label the vertices using the same notation as in the text. B, C, D, E. So this is a rectangle. That means the 4 angles are right angles. And I want to construct a square with the same area. So the first step is to extend the line BE. And to extend the line ED. This one does with a straight edge. Okay. Then the next step is to draw a circle with center at E and radius at D. So I take my compass And I want to set the radius equal to the length of the side ED. And I do that. And really, I want to see where it intersects this line. And this point I call F. All right. So we construct the point F on the line through D and E with the length of EF equal to the length of ED. So this equals this. Now I have the line segment from B to F. And with straight edge and compass, I can construct the midpoint and the perpendicular, well, the perpendicular bisector, but in particular the midpoint. And the midpoint is right there. So this is the point which is called G in the diagram in the text. Let me just emphasize, because it's very good if you have the book with you at all times, especially since it's a lightweight paperback and it's not hard to carry. So G is the midpoint of the line segment BF. And now I construct a circle where the center is at G and the radius is BF. And I see where that circle intersects the vertical line through ED, and I call that point H. And then I construct a square whose side is EH. So constructing a square with side equal to some fixed side is easily done. And so this is the point K. And I construct this square as well as I can. And this point I'll call L. And this is a square. EHLK is a square. And I claim that the area of the square, EHLK, equals the area of the rectangle we started with, BECD or BCDE. So I claim this square and this rectangle have the same areas. So how do we prove that? So Suppose we let the distance from B to G equal A. And the distance from G to E equal B. Right? So this distance is A, and this distance is B. Now, the distance from B to G equals the distance from G to F. So then the distance from B to G is the midpoint. This is G. G is the midpoint of the line segment from B to F. So the distance from B to G, let me draw this a little bit closer so it's clear where G is. Right? G is that point right there. The distance from B to G is the same as the distance from G to F, which is equal to A. So from here to here, the distance is A. From here to here, the distance is B. So this implies that the distance from E to F is A minus B. The distance from E to F. Because this plus this equals A. Something plus B equals A means that something is A minus B. And the distance from E to F is the same as the distance from E to D. That's how we drew this. We took a circle with center at E and radius ED, and where it intersected the horizontal line, that's the point we called F. So this is A minus B, and here to here is A plus B. So the area of the rectangle is equal to the height times the width, A plus B, A minus B, which is A squared minus B squared. So that's the area of the rectangle. What's the area of the circle, of the square? Well, let me draw, this is a right angle. If I draw EG, HG, this is a right triangle. H is on the circle with center at G and radius B. So this hypotenuse of this circle is A. This is B. And let me call this C is the side of the square. The area of the square is the side squared, C squared. But this is blue is a right triangle. So triangle EGH is a right triangle. By the Pythagorean theorem, B squared plus C squared equals A squared, which means C squared is A squared minus B squared. The area of the square is C squared, which is A squared minus B squared. The area of the rectangle is A squared minus B squared. So they're equal. The area of the green rectangle is equal to the area of the red square. And that's what we wanted to prove. Okay. So that is a really beautiful construction of quadrature of a rectangle. And then we saw how once you can compute the area of a square of a rectangle, you can compute the area of a triangle, because the area of a triangle is half the area of the rectangle with the same base and half the height. And if you can compute the area of two triangles, you can, well, if you can compute the area of two triangles, you can compute the area of something which consists of two triangles pasted together. And any polygon, in fact, can the area of any polygon can be computed in this sense in Greek mathematics. And let me just explain again what I mean by the area of a triangle. Suppose here you have a triangle, and this is the height, and this is the base. Compute a rectangle with the same base and half the height. The area of a triangle is the base times half the height. So this triangle and this rectangle have the same area. And from this, we can compute a square with the same area as the rectangle, and therefore the square has the same area of the triangle. Suppose you have a quadrilateral. So if you take a line through the quadrilateral, you divide it up into two triangles. This has area A1, this has area A2. And corresponding to the area A1, you can find a square with area A1, and you can find a square with area A2. And then if you construct a right triangle where the side of A1 is the length of one of the legs of the right triangle, so this square has area A1, and this, not drawn very well, has area A2, then if you look at the square on the hypotenuse, that has area A1 plus A2. So the area of this square is the area of this quadrilateral. And continuing step by step, you can take any polygon in the plane, write it down as a sum of triangles, and carry out the quadrature. So you have to think about that a little bit, or read the book carefully, which explains it very carefully. So computing areas of polygons is easy. And a problem the Greeks could not solve is compute the area of a circle by quadrature. That is, given a circle of radius r, construct a square with the same area, right? Greeks could not do this. They could not solve the problem of what we would say squaring the circle. And for any geometrically shaped area which has curved boundaries, it wasn't clear that they would ever be able to find an example, even of some area, some region in the plane that was constructed from arcs of circles. So let me give an example of, let me call this the lune of Hippocrates. A lune is something cut out by two circles in a certain way. And let me draw a picture of a lune. So how should we do this? Let's start. So make sure I have enough space. I'll start again on a clean piece of paper. So what I've drawn is going to be the diameter of a circle with center at the point 0. So let me draw a circle with this radius. Actually, I just need to draw the semicircle. Why is this not? So that is a semicircle with diameter AOB. And I draw the perpendicular, I construct the perpendicular radius to that circle. There it is. So this is a right angle, and I call this point C. And then I draw the line from A to C, and on that line, I construct the midpoint. Which is about there. And that point I'll call D. And then I construct the semicircle with center at D and radius AD. Okay. And so this is a semicircle, and this is a semicircle. And the region that I'm sketching in blue that's a region between two arcs of a circle, and it looks like a moon, which is why it's called a lune. So this blue figure is the lune, it's a lune, and this is the lune of Hippocrates. And we're going to carry out quadrature of this lune. We want to construct a square with area equal to the area of the lune. So for purposes of exposition, let's say E is just some point on this semicircle, and F is some point on this semicircle. So we're interested in this blue lune, AECF. Now, we use certain facts already proven in geometry. For example, we prove that an area inscribed in a semicircle is a right angle. There also is a theorem that says the following: if you have two circles, one with diameter little d and one with diameter in capital D, and let's say then the ratio, so call this, circle 1 and circle 2, the ratio of the areas of these circles is like the ratio of the squares of the diameters. So we call this 1 and 2. So the area of circle 1 divided by the area of circle 2 is like d squared over capital D squared. It's the ratio of their areas. So if we look at the semicircle AEC, so that's all of this line and this. So the area, semicircle was just half the area of the circle. The area of the semicircle, ADCE, divided by the area of the big semicircle, ABCF, is like the ratio of their diameters. ADCE, that diameter is AC. So that's the length of AC squared. The diameter of this circle is AB, the length of AB squared. What's the relationship between the length of AC and the length of AB? So this is a right triangle. This has length AB. This is half of it. So this is the length of AB over 2. And this is the length of AB over 2. And this is a right triangle. So the length of AC squared is 1/2 the length of AB all squared plus 1/2 the length of AB all squared. That's a 4th AB squared plus a 4th AB squared. That's a half. AB squared. So this ratio of the areas, AC squared is a half length of AB squared divided by the length of AB squared. These cancel. This is equal to a half. So the semicircle ADCE has half the area, exactly half, of this semicircle. So that means that the area of the semicircle ADCE is half the area of the semicircle ABCF, but this semicircle is divided into 2 quadrants. So half the area of the semicircle is the area exactly of the quadrant. I'll put in green. AOCF. Now, this is really very fascinating because what does this say? It says, if I take, what's the area of the semicircle ADCE? This is equal to the area of the lune plus the area of this piece ADCF. So the blue plus this bit of green is the area of that semicircle. But the area of this quadrant is the area of the triangle AOCD, or AOC, plus the area of this piece, ADCF. So this plus this equals this plus this. If you subtract this area, you get the area of the lune equals the area of the triangle AOC. And we're done. So we just proved that the area of this blue lune equals the area of the blue lune equals the area of the red triangle. And I showed a few minutes ago how to compute the area of a triangle, that is, how to construct a square with the same area as a triangle. So the square with the same area as a red triangle has the same area as the blue lune, and we're done. So that is the beautiful, beautiful, beautiful proof of Hippocrates' theorem. This is the great theorem in chapter 1. And one of the rules of this course is you have to know everything in the book. But one thing in particular you absolutely have to know is the proof of each of the great theorems in each of the chapters. So you really need to be able to carry out this construction and explain what you're doing and prove that the construction does solve the problem. Okay. Any questions about that?
Professor, can you please go down to the bottom of the page?
Sure.
Thank you. On the bottom where you said, so the area of the lune is equal to the area of the triangle AOC, correct?
Yes.
Okay, thank you.
Now, let me explain a little bit more why the Greeks were not able to square the circle. So, in a short sentence, the statement is squaring the circle is, the Greeks couldn't do it, not because they weren't smart enough, but it just can't be done. This is, let me just emphasize, this is provably impossible. So not only, so you have a circle and you want to construct a square with the same area, and it can't be done. Construction with ruler and straight edge and compass. It cannot be done. And the reason is, in some sense, similar to the reason why you can't write the square root of 2 as a fraction. So writing square root of 2 as a fraction which is another name for a rational number, P over Q, is also provably impossible. Why is this impossible? Well, let me repeat the proof. Again, this is something which you absolutely positively have to understand to be able to generalize. Suppose the square root of 2 is a fraction P over Q. So this is positive, so P and Q are either both positive or both negative, so you can make them positive, right? Just multiply by -1. So P or Q are positive, and you can always reduce the fraction to lowest terms, so P and Q are what are called relatively prime integers, which means they have no common factor. So 6 and 35 are relatively prime. They have no common factor. 30 and 35 are not relatively prime because both are divisible by the number 5. And again, you learn in elementary school or wherever you learn about fractions, you can always write a fraction in lowest terms. If you had 30 over 35, you can divide out by 5. This is 6 over 7. So these represent the same number, but this is in what we call lowest terms. The numerator and denominator are relatively prime. They have no common factor. And you can always cancel out common factors in a fraction to get an equal fraction, which is in lowest terms. So this is going to be a proof by contradiction. We want to show square root of 2 is not a fraction. So we assume or suppose that it is a fraction. You can always write the fraction in lowest terms, and we're going to show this leads to a contradiction. So if the square root of 2 is P over Q, if you divide by Q, we get P is the square root of 2 times Q. So if you square both sides, P squared is the square root of 2 times Q squared. You square the square root of 2, you get 2 Q squared. Which means, well, 2Q squared is an even integer. Of course, it's clearly divisible by 2. It's a multiple of 2. And if P squared equals 2Q squared, P squared is even. Now, you can check that if P is odd, the product of two odd numbers is odd, so P squared, which is P times P, is odd. So if P squared is even, that implies P is even. Even number is a multiple of 2. So P is equal to 2R for some integer R. So we have P squared is 2Q squared, but P is 2R, so that's the same as 2R squared. 2R squared is 4 times R squared. So we have 4R squared equals 2Q squared. If you divide by 2, you get 2R squared equals Q squared. So Q squared is even, which means Q is even. And now we have a contradiction. Because we just proved that if the square root of 2 is p over q, a fraction reduced to lowest terms, then p has to be even and q has to be even, but then both p and q are divisible by 2 and they're not relatively prime. They have a common factor. So the assumption that root 2 equals p over q leads to a contradiction. So root 2 is therefore irrational. It can't be written as a fraction.
Professor,
Yes.
when you're proving that a value is irrational, do we always use a proof by contradiction?
No, you use whatever, you can use anything you want to use. And not all proofs that certain numbers are irrational are proofs by contradiction. But this is a classical proof by contradiction. And on the homework where you have to prove that certain numbers are irrational, you use exactly the same method. Okay, let me give another example. Suppose we want to prove square root of 3 is irrational. Well, assume square root of 3 is a rational number where p and q are relatively prime integers. If you multiply by q, you get p is the square root of 3 times q. If you square both sides, you get p squared is the square root of 3q squared. When you square the square root of 3, you get 3 times q squared. Which means 3 divides p squared. And I claim, I have to prove this, that this implies that 3 divides p. I must prove this. In the case of the square root of 2, I had to show that if 2 divides p squared, then 2 divides p, or p is even. Here I have to show that if 3 divides p squared, then 3 divides p. So how do we prove this? So suppose we take p and we divide it by 3. So if you divide it by 3, you get, let's say, 3 times some number m plus k, where k is 0, 1, or 2, right? Because if you divide a number by 3, you get a remainder, which is less than 3, 0, 1, or 2. So there are 3 cases. Suppose k is equal to 1. That means p is 3m plus 1, which means p squared is 3m plus 1 squared. That's 9m squared plus 6m plus 1. That's 3 times 3m squared plus 2 plus 1. This is 3 times something and a remainder of 1. So p squared is not divisible by 3. Numbers divisible by 3 means you divide it by 3 and you get a remainder of 0. If p is 3m plus 1, it has a remainder of 1 when you divide by 3. Then p squared also has a remainder of 1 when you divide by 3, so it's not divisible by 3. Suppose k is 2. So p is of the form 3m plus 2, which means p squared is the form 3m plus 2 squared. If you square that, you get 9m squared plus 12m plus 4. That's 3 times 3m squared plus 3 times 4m, and 4 is 3 plus 1. So I can write that as factor out the 3 from the first terms, 3 times 3m squared plus 4m plus 1 plus 1. So p squared is 3 times something with the remainder of 1. So p squared not divisible by 3. So the remainder 0, 1, or 2. If p squared is divisible by 3, the remainder cannot be 1 or 2. So therefore, k has to equal 0, and p is 3m. So what we just proved is that if p squared is divisible by 3, then p is divisible by 3. So we have 3q squared equals p squared. P is this multiple of 3, 3m squared. That's 9m squared. Divide by 3, q squared is 3m squared. So q squared is a multiple of 3, which means 3q is some multiple of 3, 3 times n. So if the square root of 3 is p over q, then p is 3 times some number, q is 3 times some number. So p and q are not relatively prime, and that's a contradiction. So therefore, the square root of 3 is irrational.
Okay. Thank you.
So this is a very classical method of proving irrationality. And again, it's one of the fundamental landmarks in the history of mathematics, the existence of irrational numbers. It was a huge discovery in ancient Greece that not all numbers were rational. On the other hand, square root of 2 is irrational, but it is the root of a polynomial. If you take the polynomial f of x equals x squared minus 2, this is a polynomial with integer coefficients, right? 1 and 2. F of the square root of 2 is the square root of 2 squared minus 2 is 2 minus 2 is 0. So this polynomial has square root of 2 as a root. Suppose I take square root of 3. Square root of 3 is a root of the polynomial f of x equals x squared minus 3. So the square root of 3 is irrational, but it's still the root of a polynomial, a quadratic polynomial. Suppose I take the number, let me call it theta, square root of 2 plus the square root of 3. Is theta the root of a polynomial? Well, let's see. If theta is the square root of 2 plus the square root of 3, theta minus the square root of 2 equals the square root of 3. So if I square both sides, 3, which is the theta root of 3 squared, which is theta minus the square root of 2 squared. If I square this, I get theta squared minus 2 root 2 theta plus 4. If I take theta minus the square root of 2, make this more legible, and I square it, I get theta squared minus 2 root 2 theta plus 2. Square root of 2 squared is 2. Or in other words, theta squared minus 2 root 2 theta minus 1 is 0. Right, so let me pause for a minute. You should be able to write this down and justify every step. So we prove square root of 2 is irrational, but it's the root of a quadratic polynomial. We prove the square root of 3 is irrational, but it's also the root of a polynomial. Happens to be a quadratic polynomial, polynomial of degree 2. What about root 2 plus root 3? Is this the root of a polynomial? Well, let's see. If I let theta minus root 2 equal root 3 and I square both sides, I get 3 is theta squared minus 2 root 2 theta plus 2. If I bring the 3 on the other side, I get theta squared minus 2 root 2 theta minus 1 is 0. Let me rearrange this. I get 2 root 2 theta is theta squared minus 1. If I square both sides again, 2 root 2 theta squared is theta squared minus 1 squared. If I square 2 root 2, I get 8 theta squared. If I square theta squared minus 1, I get theta to the 4th minus 2 theta squared plus 1. Bring this to the other side, I have theta to the 4th minus 10 theta squared plus 1 equals 0. So my number theta, which is root 2 plus root 3, satisfies this equation. Or another way of saying this is that theta is a root of the polynomial f of x equals x to the 4th minus 10x squared plus 1. So this is a quartic polynomial. This is a polynomial of degree 4, and theta, root 2 plus root 3, miraculously, is a root of this polynomial. Let's see if I can show you sort of a picture of this. So I claim if you take root 2 plus root 3 and plug it into this polynomial, you get 0. So for those of you who've taken calculus at Lehman and took math 155 or 156, and were lucky enough to learn Maple, let me just confirm this calculation in Maple. So let me see if it's possible. to share my screen. So, do you see a Maple worksheet on your screen?
Yes.
Okay. So, suppose I call the number A. Oops. Let me make it bigger so it's easy to see. This number I'm interested in, square root of 2 plus square root of 3. If we're curious what this is as a decimal, it's close to pi actually, but it's not pi, but it's 3.1462 something. Then I want to define my polynomial. This is a polynomial function. F of x is going to be equal to x to the 4th minus 10 times x squared plus 1. That's a polynomial. I'm curious to see what it looks like. I could plot f of x. Oops. What's that dot doing there? That shouldn't be there. Plot f of x. There's the plot. Actually, if you see, let's load up a little bit. Yeah, that's my graph. So it looks like where this graph crosses the x-axis, it crosses the x-axis in 4 points, but this point looks like it might be 3.1462. But let's actually check. Suppose I compute f of my number a. A is square root 2 plus square root 3. F of a, that's just plugging it into the polynomial. Let's see what happens if I expand it. I get 0, exactly what I'm supposed to get. So this is just seeing visually, this is the polynomial. And at this point, root 2 plus root 3, polynomial is 0. That's kind of nice. I mean, you certainly don't need to know Maple for this course, but Maple is a very good thing to know in general if you have any interest in math or science, because in all of your physics and chemistry and so forth, it's also very valuable to have Maple, not just in mathematics. Okay, so these numbers, root 2 and root 3, and root 2 plus root 3 also, that's harder to prove.
Professor,
Yes.
can you explain again how you got negative 10 theta square?
Sure. So I have theta is root 2 plus root 3. So theta minus root 2 is root 3. Okay, is that okay? I
Yes.
just subtracted root 2 from both sides of this equation. Right.
Yeah, that's okay.
Okay, and then I square both sides. So if I take root 3 and square it, that's the same as theta minus root 2 squared. If I square the square root of 3, I get 3. If I square theta minus root 2, just by squaring, I get theta squared minus 2 root 2 theta plus 2. So do you see that this equals 3? Is that okay?
Yeah.
And if I subtract 3 from both sides, I get theta squared minus 2 root 2 theta minus 1 equals 0. I get that equation. So theta solves this equation. But it doesn't have integer coefficients. Root 2 is irrational. But theta solves this equation. That's what this says. So if I bring the 2 root 2 theta on the other side of the equal sign, I get 2 root 2 theta equals theta squared minus 1. All right, is this okay?
Yes.
Now I square both sides. If I square 2 root 2, I get 8. Right? 2 squared is 4, root 2 squared is 2, 4 times 2 is 8. So if I square this, I get 8 theta squared. But that's the same as theta squared minus 1 all squared. That's theta squared. When I square this, just by the rules for squaring, this is theta to the fourth minus 2 theta squared plus 1. And if I take this 8 theta squared and move it to the other side of the equation, I get this minus 8 theta squared. I get 10. Theta to the fourth minus 10 theta squared plus 1 equals 0. So that's where the 10 comes from.
Okay. Thank you.
So, yeah. So you tend to think as you take more advanced mathematics, you have to know a lot of fancy stuff like calculus and differential equations and vector analysis, but you also need to know arithmetic. And it may be nowadays everyone spends so much time doing their arithmetic on calculators, they don't know how to do it, or they lose the ability to do it easily by hand, but it is an important ability to have. Okay. So we had that square root of 2, square root of 3. We didn't prove it, but it's also true that root 2 plus root 3 are irrational numbers. But are roots of polynomials with integer coefficients. And a number that is the root of a polynomial with integer coefficients is called algebraic. So an algebraic number is a root of a polynomial with integer coefficients. So root 2, root 3, root 2 plus root 3, they are irrational, but they are algebraic numbers. And just as one could ask whether every number is a fraction, and the answer was no, we can ask, is every real number algebraic? So if you have any number like the fifth root of 19 minus 2 square root of 7 cubed plus 31, is this algebraic? Is that the root of some polynomial? Or take the area of a circle. Is pi algebraic? Is log 2 algebraic? Right? Is every number algebraic? And it took 2,000 years, but in the 19th century, there is the following theorem proven: not every number is the root of a polynomial, no matter how complicated the polynomial. Not every number is the root of a polynomial. Right. Such numbers are called transcendental numbers. So in some sense, they transcend algebra. These are numbers that no matter how sophisticated, complicated, or big a polynomial you choose, let me spell it correctly. Transcendental numbers. So these numbers, in some sense, transcend algebra. They're not the roots of any polynomial. And E is transcendental. Pi is transcendental. Log 2 is transcendental. And these are hard theorems to prove, well beyond what one could teach in an undergraduate class for math majors even. But this is also one of the most important results in the history of mathematics, that there are some numbers that are not the roots of any polynomial. And in particular, pi is transcendental. Now, and if pi is transcendental, also square root of pi is transcendental. Suppose you had a circle of radius 1. So what is the area of the circle? Well, the area of a circle was pi r squared. So if r is 1, r squared is 1, the area of a circle of radius 1 is pi. If you have a square of side x, the area is x squared. And if you had a square with the same area as this circle, the area of x, the area, which is x squared, would be equal to pi. So x would be the square root of pi. And one can show that if you can construct with straight edge and compass a square of side x, then this number x is algebraic. So if you're using a straight edge and compass, you're basically doing operations which have to do with a straight line is like ax plus equals b, and a circle is like x squared plus y squared equals r squared. Then x is algebraic. If the square root of pi is transcendental, which means not algebraic, that proves you cannot square the circle. And this is something discovered. It was a huge accomplishment near the end of the middle to late 19th century, that transcendental numbers existed, and that pi and the square root of pi were transcendental, so you cannot square the circle. Very few explicit examples of transcendental numbers are known, but it is a mysterious, perhaps mysterious fact that indeed almost all numbers are transcendental. If you look at the number line, 0, 1, 2, you have fractions, a half, 5/4, and so forth. You have things like square root of 2 that are algebraic. But if you look at all the numbers on the number lines, almost all of them are actually transcendental. The numbers you know and love are almost all algebraic. The only exceptions really are things like e and pi. But in fact, almost all numbers are transcendental, and there's no way to even write them down. It's a very curious state of affairs. Okay. So that pretty much covers chapter 1. And there's some homework for next week. I have almost always Zoom sessions Tuesday and Thursday evening at 7 when anyone in any of my classes can log in and ask questions. In particular, you can ask for help with homework problems if you like. And I would encourage you to take advantage of them because, I mean, if no one logs in, I hang around for a while, half an hour maybe, and then I just go off and drink my coffee. But I'll normally, I'll always be there, and I encourage you to stop in to the Zoom session and ask questions. Okay. Anything else before we quit for the morning? Okay. Have a nice weekend all. Be back on Monday.
Professor,
Yeah, go ahead.
are you gonna post this video to YouTube?
Oh, yeah, I mean, the video for the first lecture is already posted.
Okay. Thank you.
Okay. All right,
Oh, I do have a question.
go ahead.
For submitting the homework, should we submit it as a PDF or a Word document, or do you have a preference?
Well, you can't really do math in Word. Just write it out. You do need a printer that converts, where you can go to print and choose the option to save as a PDF. But just write it out by hand and upload it as just a PDF document. Now, there will be later in the semester some short papers to write. And I don't want a paper written out in longhand. A paper, use Word or any other, program on the computer for creating a file. And I think it used to be the case that Lehman students and CUNY students could get Microsoft Office for free. I'm not sure if that's still the case, but it had been that everyone could get for free Microsoft Word. And that's a program that a lot of people use. But essays, papers, not longhand, not written out by hand, but homework, certainly you just write out by hand, convert it to a PDF file and upload it. I mean, don't wait. First of all, Microsoft Word is a horrible way to use it to write mathematics. One of the greatest programs, computer programs ever written is a mathematical typesetting program called LaTeX, which you can get anywhere on the internet for free. It's never, but it takes a while to learn it. But it's enough to write out solutions by hand, convert it to a PDF, and upload the PDF to assignments.
I was asking because what I was doing was I was writing it out on paper, and then I was like scanning that, and then I would put that on the Word document and then turn that whole thing into a PDF and send that to you.
Well, whatever you want, but it's easier. I mean, it usually takes less time if you've written it out by hand, just to scan it in your printer and to get a PDF and upload that. You don't have to go through, Word is the intermediate state.
Okay.
I mean, I truthfully, I never use Word. I only use LaTeX, but 99% of the rest of the world uses Microsoft Word, but I don't,
Okay.
I have a principle, which is never use anything by Microsoft, but that's it's usually someone else has something much better, but it might be more. But in any case, it's completely up to you. But I would say do whatever is quickest and easiest.
Okay.
The important thing is to work on the problems, and how you get the PDF to upload to the assignment section for grading is up to you.
Okay. Okay. Thank you.
Okay. Anything else?
Yeah, I have a question. What's the difference between Maple and something like Desmos?
Like what?
Desmos?
Never heard of it.
Okay, so what exactly is Maple? It's just a program where you can, it's like a calculator, or?
It's infinitely more than that. It's a mathematical, it's a computer algebra program. Again, it's one of the great programs ever written. If you buy it, it's expensive, but CUNY students can get it for free. You go to there's a online, I can upload the information to Blackboard, but you can download Maple it comes with like a 1-year license. You get it for a year, but every year you can get it again. You get it free from CUNY, but you have to learn how to use it. It's like any program, but it does everything: calculus, algebra, number theory, very sophisticated mathematics, solve differential equations, solve partial differential equations. It's an unbelievably powerful program. It's not unique. There are other programs that are comparable. There's something called Mathematica. There's something called MATLAB, and there are other ones as well. So nowadays there are a lot of extremely good, high quality computer algebra programs. Maple is the one that I and several people at Lehman use when we teach Math 155 or Math 156, which is the lab that goes with Calc 1 and Calc 2. And not everyone uses Maple, but in any case, Maple is the one that I recommend because I know it's excellent and it's fairly easy to learn how to use, but it does take a few hours.
Okay.
What you saw me do with that, when I sketched the graph of the polynomial and plugged in that root 2 plus root 3, that was very simple to do in Maple.
Okay. What other classes do you teach in Lehman?
Well, this semester I'm also teaching vector calculus, third semester calculus, Math 226. And I'm also teaching 2 calculus labs for second semester calculus. So it's Math 156, which are Maple classes that I teach. But those 2 classes, the math labs, the Maple labs are taught, like this is a hybrid class, but the Maple labs are 100% Zoom classes. So the lectures for the semester are already videotaped. I've already videotaped them and posted them on YouTube. But I do have office hours for students in those classes as well. But the 2 classes where I lecture like this are history of math and vector calculus.
Okay, thank you.
If you
So you're
download
not
Maple and want to
teaching
learn how to use
number
it,
theory?
just go to YouTube and you'll see I have lots of in my math in my YouTube channel. There are playlists for Math 156 for Maple, which start from the beginning.
Professor, you're not teaching number theory this semester
No,
and linear algebra?
no. Normally people teach different courses every semester. So last term I taught linear algebra and number theory. This term I'm teaching history of math, vector calculus, and I usually also teach a couple of sections of Maple calculus lab. All right. Okay, I'll be back on Monday. But I'm
Thank you,
also on
Professor.
Zoom tomorrow, Thursday at 7 p.m. if you have a question or want me to do some homework problems. Happy to
All
do
right.
it.
Thank you, Professor. Have a good day.
All right, thank you. All right, bye all.
Thank you.